Hi, my name is Nick Schragal. I am a senior astrophysics and applied physics student here at UAH. This summer, I did the project Hunting for Ultra-Diffuse Galaxies in the Hubble Space Telescope Data Archive with Dr. Ming of the Department of Physics and Astronomy. You're probably familiar with what a galaxy is, but may never have heard of an ultra-diffuse galaxy. I wouldn't blame you, because they were only classified in 2015. Ultra-diffuse galaxies are a relatively new class of galaxies characterized by their sizes being greater than or equal to that of the Milky Way and having surface brightnesses that are extremely dim for a galaxy that size. We measure the size of the galaxies in their half-light radius. The half-light radius is the radius in which half the galaxy's light is contained. For ultra-diffuse galaxies, that minimum radius is 1.5 kiloparsecs. Surface brightness is the other characteristic, and for ultra-diffuse galaxies, that must be greater than 24 magnitudes per square arcsecond. That is, brightness per area. Now, you might be wondering why surface brightness needs to be greater than 24 instead of less than 24, as you might expect. That's due to the quirks of the astronomy magnitude system, where the larger the number, the dimmer the object. Thank the ancient Greeks. Now, you have two examples behind me. This right here is not a UDG. As you can see by this scale down here, which is 1 kiloparsec long, this galaxy's diameter is barely 1 kiloparsec. Its half-light radius is nowhere near the required 1.5 kiloparsecs. Over here, on the other hand, this is the UDG DF44, Dragonfly 44, for the telescope that discovered it, of course. You can see the scale down at the bottom. The half-light radius of this bad boy is 2.4 kiloparsecs, and its surface brightness is greater than 24 magnitudes per square arcsecond. So this is a UDG, and this one is too small. Now, UDGs vary wildly in their dark matter content, which is a little interesting. You find some UDGs that are almost completely dominated by dark matter. And on the other end, you find UDGs with almost no dark matter to speak of. That's a little strange, but it's something that can be studied, that needs to be studied more and more and more. Now, there are a number of different theories behind how UDGs came to be and how they form in their clusters. One hypothesis is tidal gas stripping due to interaction between these UDGs and other larger galaxies in their clusters. Another is they used to be dwarf galaxies that had a really high angular momentum. And another is stellar outflow, gas emitted by stars, coupled with just this loss of gas that ended up quenching the galaxies. Galactic quenching is when you lose all the gas that can create stars, and thus you stop forming stars. Simple as that. So now that we know what a UDG is and kind of what we're looking at and what is being looked at currently with their formation processes and with their dark matter content, let's dive in and look at how we can pick these out of our data. Since they're really dim and very hard to see, at least with the naked eye. This image over here, this image is a wider field of DF44. This is DF44, this blotch right in the middle. Astronomers use a program called Source Extractor, which has been modified and adapted to work in Python. It now has a Python package called Source Extractor for Python, or SEP, as I'll refer to it. Using SEP, we can identify the various sources, the various objects, galaxies, stars, and whatnot in this image. And one of the output files of SEP is found right here. If you want to know more details on the parameters that go into SEP, refer to the poster. This is one of those output files referred to as the segmentation map. The white blotches represent the objects SEP identified in the image. And this one right here in the middle, this is DF44. You can see it right here as well. Now you'll notice that there is an extra little blotch right up here, an extra little lobe. That is partly due to this star right here causing that little lobe. But don't worry, this bigger blob is DF44. So we can identify these with Source Extractor for Python rather. And with that done, we can then go on to verify that these objects are actually UDGs, as we did with DF44. Now DF44 is also pictured right here. You'll notice that the scaling on this image is vastly different, and you can barely see the haze of DF44 in here. Now usually you can create what's called a light profile for a galaxy. A light profile is a model for the brightness of a galaxy in the most basic terms. What you can do is you can draw some ellipses that all are isophotes, lines of equal brightness, compose those all together and create kind of an ellipse-looking thing that mimics what this galaxy's brightness is. And from that, you can make measurements really easy. However, because these UDGs are so dim, that's not really possible here. Whenever you take the AstroPy packages for doing that isophote fitting and model making, it does not work. It doesn't see this as a galaxy, it sees it more as background noise. So we had to figure out a different way to do it. Instead, we did what I like to call iterative aperture photometry. This red ellipse here illustrates what we're doing. We draw this ellipse on the image, which encompasses the entire galaxy, and then we take that ellipse and sum all the pixel values within it. Once we sum all those pixels, we put them in a chart, we put them in a table, in a list, array, whatever, and we compress, we shrink the ellipse just a little bit by a pixel. Then we redo, and we resum, and we keep doing that until the ellipse shrinks to 0. Once the ellipse shrinks to 0, we end up with this plot here. This is our half-light radius. This is our half-light semi-major axis plot. On the y-axis, you have the flux in electrons per second, as that is the unit for the pixels in the image. And at the bottom, the semi-major axis in pixels. The black dotted line represents the half-light semi-major axis. That is 133 pixels, or 3.1 kiloparsecs, for DF44. Now you'll notice that is the semi-major axis, not a radius. In order to get the radius, what we do is we compute the semi-minor axis of these ellipses, based on the eccentricity and the semi-major axis, and then we get a geometric mean of the semi-minor and semi-major axes. And that is what gives us the half-light radius for DF44 of 2.4 kiloparsecs. This is common. This is what we can do for other UDGs. Draw those ellipses and get this graph and plot it, and then find our halfway point. You can see it starts to tail off here, which is showing us that the galaxy is pretty much done at that point. We're getting into other stuff outside that. So that is how we get our half-light radius. I also mentioned surface brightness, but surface brightness is fairly trivial. There is basically a formula for surface brightness. You can just plug and chug, and you get your answer. And as it turns out, for DF44, that surface brightness does check out. It is greater than 24 magnitudes per square arcsecond. The details on that can be found in the poster. Now, with these UDGs, we can start to understand better intercluster dynamics within these galaxy clusters. For example, the earlier image I showed you of this little guy in here, this little dwarf galaxy, this is in the Coma cluster, where there have been found many, many other actual UDGs, much, much larger than this one. And we can use these to further understand also galaxy formation, particularly with UDGs themselves, and the nature of dark matter, why there are some that are so dominated by dark matter, and why there are some with very little. And that can help us kind of understand better how galaxies form and how a galaxy cluster interacts with itself. So with that, that is all I have today. Thank you very much for watching, and I hope you enjoyed the poster.